Bismillahir Rahmanir Rahim. Assalamu alaikum, dear students. We are now starting the third lecture for 7th week of wireless and mobile communication. In our previous lecture, we concluded our discussion on the large scale path loss modeling, large scale modeling for the wireless channels. In today's lecture, we are starting discussion on small scale modeling. Basically, there are two things. This small scale variations, they generally occur because of multipath effect in wireless communication, and this variation, this sudden variations, they are known as fading. So from today's lecture, we are starting the discussion on small scale fading and multipath. From the point of view of our textbook, actually we are now starting the fourth chapter from the textbook. For those who have third edition of the book, it's chapter 5 in third edition. Okay, so let us start the discussion with defining fading. Fading, the term fading is generally used to refer to rapid fluctuations that we observe in the received signal over a short interval of time or short travel distances. So it is possible, especially in wireless communication, that even if you move for a very short distance, maybe of the order of centimeters, and you see a significant change in the received signal strength, and that rapid variations over small distances or short interval of times, these rapid variations, they are known as fading. So how does this fading effect occurs? The main phenomena that accounts for fading is the multipath effect. Actually, what happens, because in wireless environment, the signal has to go through the free space, so it can take any path, and during that propagation, signal often gets reflected from different objects, say buildings or cars or other objects in the wireless environment. So those after reflection, the signal is received at the receiver side. So at the receiver, we receive multiple copies of the transmitted signal. So those multiple copies, because they come from the different path, so they generally arrive at different times, because the time of propagation is actually dependent on the path length. The longer distance has covered the signal component which has covered the longer distance, it will take longer time to reach the receiver. So those components which come through a relatively smaller paths, so they arrive earlier than those signal components which take relatively longer path. So generally we see that we get the multiple copies of transmitted signal at the receiver side, and when we get these multiple copies, so generally we see these three important effects which we observe at the receiver of a wireless channel. First of all, we observe rapid changes in the signal strength, and those rapid changes can be observed even if we travel for a very short distances, say for example of the order of centimeters. If we travel few centimeters, you can see a rapid change. Or if we observe the signal for a very short period of time, maybe less than a second, so even for short period of time, you can observe rapid changes in the signal strength. Second important thing that we observe in that received signal is that there is a change in the frequency of the signal as well. So we sometimes observe that the received signal frequencies are somewhat different than the frequencies that was transmitted. Third important thing is that because we generally have multiple copies of the same signal received at different times, and when we add up together, so the overall signal gets spread out in the time. For example, if the signal transmitted signal was for 1 millisecond, the multiple copies when it's received at the receiver, so you may see that the signal was of maybe 1.2 milliseconds. So generally the signal that is received at the receiver, it gets spread in time. So because of this spreading in time, generally one bit of the signal it gets smeared into second bit. So different bits, they get smeared into each other, and this smearing into one another it causes interference in different bits. This type of interference is commonly known as inter-symbol interference. For short, we write it as ISI. So ISI is the term which we refer to the interference that is caused between bits when the different bits they spread in time and get smeared into each other. So because of the effect of the wireless channel, we can see this smearing and inter-symbol interference as well. So these are the three important effects that we generally observe because of this multipath effect. Okay, the fading signal generally occurs because the fading in the signal is generally occurs because the signal has to reach the receiver by reflection from different objects, for example ground or surrounding building, or it may get scattered from different objects, say for example trees or people or poles. So this scattering and reflected waves, when they add up together, so they give rise to random fading. And we generally also observe multiple copies of same signal. In most cases, the line of sight path is not available in wireless signals. So generally we are interested in extracting the first multipath component, because this first multipath component, because it's reaching earlier, so it takes a shorter distances, and because of shorter distances, generally the first component is the strongest component in the multipath signal. So first multipath signal that arrives at the receiver is normally considered as the desired signal. Secondly, even if the line of sight is not available, but because of this reflections from different sides and scattering from different objects, it also allows services even if the receiver is obstructed. So even if the receiver does not have a clear direct component from the transmitter, even in that case we can get the received signal because of the reflections coming from the cluttered environment. This effect of fading does not only comes from the effect of multipath. Actually, this fading effect also comes from the movement of transmitter and receiver, because the wireless equipment or mobile equipment is generally made to support the motion of the objects, and because the motion is there in the environment as well, because of the different objects in the environment, they are also moving. So relative motion of transmitter and receiver, as well as the motions of different objects in that environment, they also cause this fading, because at different instances there are different types of reflection, and motions also cause some changes in the frequency as well. So it also results in this fading effect. If we try to summarize what type of fading effect would we see at the receiver side, then generally what we see that when the components they are added at the receiver, they give rise to random amplitudes random phases and random direction of arrival. So these multipath signals, they actually distributed randomly in amplitude, phase and direction of arrival, and because of the randomness coming from these multipath components, the overall received signal becomes random. So at the receiver side, when we add those multipath components, so we need to have this vector summation, and that vector summation of those multipath components, it leads to constructive or destructive interference at the mobile receiver when the receiver moves in space or with respect to time. So if we observe at different times, so we see different types of interference. If there is constructive interference, we generally see high amplitudes or high received power. If it's a destructive interference, so we generally see low amplitudes or low received power. Similarly, if the mobile equipment is moved in the space, even for a shorter distances, so we can see the variations in the received power. Say for example, if the received signal the mobile equipment, it moves for few centimeters, say for example it moves 7 centimeter for 1 gigahertz, you can have a variation of 1 milliwatt to 10 to the power minus 6 milliwatt. So you can see a variation of the order of 10 to the power 6. So at some instance you may get relatively very high power, and at other instances you may get very low power because of the destructive interference of these multipath components. Whenever a user is stopped at this deeply faded point, which corresponds to the low amount of power, the signal quality becomes very bad. So generally those deep fades, they are attributed with the poor signal quality. But if the user moves a bit, he or she may observe rapid increase in power because if it moves away from the deep fade point, so eventually it will get more signal strength. Even if the user remains standing at the deep faded point, the signal quality may change because the overall environment is actually changing, because in the environment the things are moving. So those movements in the environment also change the fading characteristics. So even if the user is stationary at one point, we can observe variation in the received signal when we observe for a shorter amount of time. This phenomena can also be seen among two different users or two different antennas. Say for example, if two antennas are separated by a very short distance, say for example maybe 7 to 10 centimeters, both of them may experience different signal strength. One of the antenna may get maybe in the deep fade and may get a lower signal strength, and the other antenna may get a relatively very high signal power with good signal quality. So this fading phenomena is actually observable at very short distances and short interval of time, and generally results in rapid fluctuations in the received signal strength. So you can see this is a plot for how we see the fading. If we combine this fading phenomena with the previously discussed the large scale path loss modeling, so generally fading occurs around this path loss. So this first curve here, it shows the long-term fading or path loss. The slow variations, they generally occur because of the shadowing, and around this shadowing you would see a rapid fluctuations, which is generally referred to as short-term fading. So say for example, if you see this curve, this dark line here, this one, this line is actually referring to the path loss or long-term effect, and you can see that this fading is actually superimposed to this line, so the fading variations are observed onto the long-term variations effect. So at these points where you have very low signal strength, they are actually referred to as deep fades, because the signal strength at those points would be very low, and eventually you will be having very poor signal quality. So this was the discussion related to the fading. What is the fading? Fading is actually the small scale variations that we observe in the wireless receiver. Let us now discuss what are the physical effects which influence the fading in mobile radio channels. So there are different physical phenomena which cause this fading effect. First of all, the most prominent phenomena which causes this fading is multipath propagation, because the signal in wireless channel, it can take variety of different paths, and generally the signal is received at the receiver after getting reflections from different objects and coming from the different directions. So generally those multipath component or multiple reflected components, they are received at the receiver and they are added to get an overall signal. In most cases, the number of these multipath components or the strength of those multipath components, they are random. So generally those randomnesses, when random number of multipath components and random instance, when they add up together, so they give those random fluctuations which we name as fading. Second important thing is that the multipath components which are coming from different paths at the receiver, they generally have different time delays. Normally the signal which is taking a longer path, it goes through a longer time delay, and those which come from line of sight path or from any other shorter distances path, so they generally have shorter time delay. So these multipath components, they are having different time delays associated with each of them. So so eventually when these different delayed components, they add up together, they cause those random fadings. In discussion of various environments, while discussing the path loss modeling, we divided the environments in three different categories: urban, suburban, or rural areas. Even this categorization also affects the small scale fading, because urban areas, they are attributed with many buildings which are distributed in space, so it's a highly densely situated building. So you when a signal propagates through that urban environment, so it will have lots of reflection, because the number of buildings is high in that environment. So generally we have large number of strong multipath signals at the receiver, and because the buildings are situated close to each other, so the delay is almost the same for each multipath component. So generally the most of the components, they arrive with relatively shorter time delays, and few components, they may arrive with the larger time delays. In suburban environment, because the building density is relatively small, in that case the number of strong multipath components is maybe is moderate or small number of strong multipath component, and similarly we have a moderate amount of delay between different components. In the rural environment, because there are low number of buildings and there are very few reflection possibilities in those types of buildings. So eventually we would see few number of multipath signals. Generally you can characterize them as line of sight and ground reflected components, and those components would be associated with some delay. So first of all, the most important phenomena which causes fading is multipath propagation. Another phenomena which causes this fading is the movement. Actually, the mobile equipment, it also moves with certain speed, so there is a possibility that mobile equipment is moving. You may remember that we have a phenomena which is caused a Doppler effect. Say for example, if a car is moving at certain speed and it's blowing its horn, in that case the frequency of horn is likely to change whether the car is moving towards you or away from you. That variation in the frequency is known as the Doppler shift. Similar phenomena occurs in the mobile equipments, because mobile equipments, they are also communicating with each other at certain frequencies, and whenever those mobile equipments, they are in motion, they generally cause variation in frequency. The phenomena is same, the Doppler phenomena, because whenever there is a motion of a frequency generating signal, there will be certain variation in the frequency. So that variation in the frequency is generally known as Doppler shift. So this motion of mobile components, it causes a Doppler shift, and eventually that Doppler shift also causes the fading in the mobile radio channels. Secondly, because different multipath components, they arrive from different directions and different reflections, so there is a strong possibility that different multipath components, they exhibit different frequency shifts. So Doppler variations that are observed in different multipath components will be different with respect to each other. So different component would have different amount of frequency shifts associated with them. This Doppler shift does not only comes from the motion of mobile, it can also arise from the motion of surrounding objects. If the speed of surrounding objects is high, in that case those objects can also cause the Doppler shifts. So say for example, if a stationary user is standing near a highway where there are very fast moving vehicles, so in that case, although there will be no Doppler shift because of the user, as the user is standing, but still the different multipath components would be having some Doppler shifts because they are coming from the reflections from those high speed moving vehicles. So those vehicles or those movements in the environment, they also cause the Doppler shift. But generally this Doppler shift caused by the surrounding objects is small, and it's considerable only if the speed of those objects is greater than the speed of the mobile. But for our case, in most of the cases, the mobile speed is relatively higher than the speed of objects. So in most cases we do not bother about this motion of these surrounding objects, but in some cases, like I gave the example of a stationary user at the corner of a highway, in certain cases you may be interested in calculating the speed of surrounding objects as well. So second important phenomena which causes fading is the movement, the motion which occurs in the environment or in the mobile equipments. Third important phenomena is the bandwidth. Bandwidth is also a very important phenomena. Actually, the wireless channel, the overall behavior of wireless channel is that of a filter. You can think of a wireless channel as it's a filter, as whenever we pass a signal through a filter, so that filter also causes some changes in the signal. Similarly, whenever a signal passes through a wireless environment, so that wireless channel also causes some changes in that signal depending on the channel bandwidth. So there are two important bandwidths that we generally consider. First one is the signal bandwidth, and second one is the bandwidth of that mobile radio channel, or MRC. So mobile radio channel bandwidth and signal bandwidth, their relationship is very important. Uh, if the mobile radio channel has sufficiently large bandwidth and signal bandwidth is small, then we generally do not see the distortion effect caused by this filtering caused by the channel. But if the channel bandwidth is close to that of the signal, or smaller than that of the signal bandwidth, in that case we would see the rapid fluctuations or distortion in the signal. So this relationship between the channel bandwidth and signal bandwidth, it will determine that if the small scale fading is significant or not. Secondly, this fading, it will determine that if the time distortion or intersymbol interference is significant or not. If the variations in the signal, it is causing some intersymbol interference or not. Typically, a mobile radio channel, it can cause distortion as well as small scale fading. Both phenomena can be possible, but in most practical cases we generally see one of the phenomena at a time. So if there is distortion or ISI, in that case the effect of small scale fading is generally negligible, and if small scale fading is significant, in that case the distortion caused in the symbol or ISI caused in the symbol is generally negligible. So this is the third, rather fourth important phenomena which would cause the fading in the mobile radio channel. So we have these phenomena which causes the fading to occur in the mobile radio channel. The first one is the multipath propagation, second is the speed or movement of the mobile, third is the speed or movements in the surrounding objects, and fourth one is the bandwidth of the signal which is used for communication purposes. So now the question is, how can we characterize a wireless channel, or how can we mathematically model a wireless channel? So channel modeling is actually a very critical step in the design of communication system, because channel modeling, it gives you an insight what would happen when the signal would propagate from a certain channel. So the properties of the channel, they generally determine the type of encoding that we need to use, the type of modulation that we need to use. So from the transmitter and receiver side, the different components at the transmitter and receiver, they are designed in order to meet the channel properties. So in order to determine those channel properties, it is critically important to model the channel properly. Secondly, as I said, the channel model is generally characterized as a filter, because it provides a relationship between a transmitted signal and the received signal. So it has a type of filtering effect which transforms that transmitted signal into a received signal. So we can calculate a transfer function, or that filtering effect that relates the input and output of the channel. The channel modeling also impacts the design of cells in a cellular system. For example, cell radius, as we discussed previously as well, how much loss would be there in the channel, it determines how long the signal would propagate before it becomes undetectable. So it determines how much radius for a cell we can use. So this channel modeling, proper channel modeling, also helps us in designing the cellular system. It does not only provide information about cell coverage area, but also gives us a hand of statistics, also give us insight onto the behavior of the wireless channel at the boundaries of the cell. So cell fringe coverage is also determined by these channel models. So there are different types of mathematical models that are used to represent channels. As we know that the channel is characterized as a filter, so channel has a filtering effect, as well as the channel adds some noise to the system. So we have two important phenomena which are needed to be incorporated in the wireless channel. First one is the filtering effect, and second one is the effect of noise. So the simple mathematical models that we commonly use are these one. First one is known as additive white Gaussian noise channel, or AWGN channel. Second one is the linear time invariant channel, or LTI channel, and third one is the linear time variant channel, or LTV channels. So let us discuss briefly each of these channels. So we start our discussion with additive white Gaussian noise channel. Perhaps this is the most simple mathematical model for the channel. In this type of representation, we assume that the signal is only affected by the noise. So whatever we transmit at the transmit side, it will be received at the receiver with contamination of noise. So noise gets added to that signal and we get the received signal. So mathematically we represent received signal as the transmitted signal plus this NT is the noise signal. So you can see that there is no specific filtering effect from the channel. So basically this model is showing that where the channel does not significantly degrade the signal quality, and we only see the effect of noise at the receiver side. The term AWGN is actually referred to the case where, because the noise that we consider is additive to the signal, because the noise gets added to the signal. Secondly, the noise, the statistics of noise is Gaussian, so it follows Gaussian distribution. The white noise is, from power point of view, the white noise is the one where you have constant power spectral density, or constant power for each frequency component of the noise. From the time domain point of view, that this white noise represents that two different samples of the noise, they are independent to each other. So this mathematical model, that noise at different instance of time, they are independent. So if you are getting a noise, let's say for example noise sample now or after 1 second, there will be no correlation, no dependence on these two samples. So mathematically they are called independent identically distributed Gaussian random variables. So this is a graphical illustration of this AWGN channel. A signal goes through an adder where the noise gets added to the signal and we get a received signal. Generally this ST is deterministic, but noise is random, therefore this received signal would be random. Okay. So this AWGN channel, it only includes the effect of white Gaussian noise, which means that noise is independent in both time and space domains. So different samples of the noise, they are independent to each other. Mathematically, because noise is a random variable, so it is represented by a probability density function, or a PDF. So noise, this noise seems to have the PDF of Gaussian distribution, and because they are independent, so from the property of probability density function, the overall PDF of the product of two noise samples would be equal to the product of individual PDFs. Similarly, if we find the expectation, because the independent noise distribution, they are also uncorrelated. So the two noise samples, they are uncorrelated to each other. Mathematically, this uncorrelation is represented with this notation, that whenever we try to find the expectation of a product, or we try to find correlation, so this product will be equal to product of individual expectation or individual average values. So the noise components, they are independent as well as uncorrelated. Actually, from the point of view of mathematical definitions, if two random variables, they are independent, they are also uncorrelated. But the reverse is not generally true. If two samples are uncorrelated, they may or may not be independent. But for the cases of Gaussian distribution, because the noise is actually a Gaussian noise process, it follows Gaussian distribution, both possibilities are true. So if it's independent, they are uncorrelated. If it's uncorrelated, they are independent as well. So this is the property of Gaussian distribution. Okay. One important thing which is mentioned in a note here, sometimes we do not have these uncorrelated samples. Although in most of the cases in wireless communication we do not encounter in this problem, but in order to complete the discussion, I have also included this thing as well, that if the samples are not uncorrelated, so there is certain correlation. Mathematically it will be represented by this relationship, that this correlation, that is expected value of product of these two, would not be equal to the product of individual expectations. This is called additive colored noise. Sorry, this is generally called additive colored noise, where we have some correlation between two different noise samples as well. So this is also possible, that in some cases we have colored noise, but for the purpose of this course, we will be focusing on this white noise. That means we have identical independently distributed wireless channels. So the noise samples that we collect at different instances would be uncorrelated to each other. So this is the first type of wireless channel, which is named as additive white Gaussian noise channel, which is commonly used in variety of different analyses, and it's ideal in the sense that it does not have any specific filtering effect coming from the channel, and the dominant phenomena is the noise only. So the overall behavior of the received signal is determined by the behavior of the noise that is being added to the transmitted signal. So this is the first type of wireless channel. Then we'll be discussing about the other types of wireless channels, that is linear time invariant channel and linear time variant channel, in our next lecture, inshallah. So we stop our discussion here, and we will leave the discussion on the LTI and LTV channels for the next class. So for today's lecture, we actually talked about the fading phenomena. We talked about what is the fading phenomena, and we discussed different factors, physical factors, which give rise to the fading in the mobile radio communication channel. And later on we started discussion on the wireless channel models, and we briefly talked about the additive wide Gaussian noise channel, or AWGN channel. So we stop here, and we'll continue discussion on LTI and LTV in next class. Thank you all.